On this page, we're not going to go into details about the ANOVA test. We'll just look at the idea behind the ANOVA test, the ANOVA F test. Before we move on to the next steps in the hypothesis test, which will be checking conditions and finding the test statistic, we'll discuss the logic of the ANOVA F test using our example. So as before, we will make an inference about population means using sample means Y1, Y1 bar, Y1, Y2 bar, Y3 bar, and Y4 bar. Those are the sample means. So mu1, mu2, those are all the population means, but we'll make inferences about the population means, which we might not know by looking at the sample means. Y bar 1, anyway. So like I said, we don't necessarily know the mean of each population, mu1, mu2, but we'll kind of infer what we think we can come to conclusions about by looking at the sample mu, or sorry, the sample mean, Y1 bar, Y2 bar, et cetera, et cetera. So we'll find the sample mean frustration score for each of the 35 students in each of the majors. Let's look down here. Now, remember they said that 35 students from each of those 4 majors, business, English, math, and psychology, were asked what their mean frustration score is. And let's see, it said that the average, where 1 was low frustration, 20 was the highest frustration. For business majors, the average was 7.3 between 1 and 20. So not too bad. And then for English majors, it was a little higher, 11.8. So more frustration on English majors parts than business majors parts. Math majors, more frustrated than both so far, 13.2 between, that's a little closer to 20 than 1. But psychology majors seem to have more frustration level than anybody else. 14 was the highest. So we need a way to judge the variation in the sample means from our 4 independent samples to determine if the differences are statistically significant. First, if we find that the 4 sample means are not close together, or at least one deviates substantially from the others, we say that we have evidence against the null hypothesis and the population means are not equal. Otherwise, if the sample means are close together, we'll say that we do not have evidence against the null hypothesis, i.e. the differences in the sample means are not statistically significant and the sample means could come from populations with equal means. Now we'll look more specifically at the F statistic. Okay, the test statistic for the ANOVA hypothesis test is called the F statistic. It is named after its inventor, Sir Ronald Fisher. So F for Fisher, F statistic. It measures the variation in sample means relative to the variation in the data within each sample. The F statistic is very complicated and we will not compute it by hand, but in essence, it is the ratio of variations. Hence the name analysis of variance, ANOVA. So the F statistic is the variation in the sample means, how much they vary, which, that's written in words, so you kind of have an idea of what it is, but the formula is complicated, divided by the variation in each sample, which is also something complicated. So in this class, we won't compute these F statistics by hand, but just that way you know the idea behind it. Maybe if you have to take more statistics classes, you'll get more into detail about the formulas themselves. Now we ask, why does the F statistic take into account the spread of the data within each sample? This is an important question. To better understand the F statistic, we will examine 2 possible scenarios for our sample. 1, in each scenario, the sample means are the same. For example, business, 7.3, English, 11.8, math, 13.2, psychology, 14.0. No matter what in each scenario, the sample means are the same. Therefore, the variation in the sample means is the same. Or secondly, it could be that the scenarios differ in the amount of spread in the data. We will see how the spread in the data influences our perception of the variation in the sample means. Below are box plots of the frustration scores of the 35 students in each sample. You can kind of compare them because there are 4 next to each other. Let's kind of scroll down and see those while we're talking about it. In each box plot, the red dot marks the sample mean. Based on the box plots, which scenario do you think represents samples that come from populations with different means? So notice it shows that in the bottom box plot, the interquartile range is not very large. You got like the middle half of the data is more tightly packed for psychology versus here, and then same for the bottom one here. It's higher, it's between 10 and 20. This one's kind of between 20 and something lower than 10. So you definitely see a wider variation in scenario 1 than in scenario 2. Okay, let's scroll down. Let's see. Which scenario suggests that the samples come from populations with different means? That would be scenario 2. because in both scenarios, the sample of business majors have the lowest sample mean, but we need to consider the variability in the data. Let's compare typical scores in the middle half of each distribution represented by the box part of the box plot. In the bottom scenario, scenario 2, typical business majors have lower frustration scores than typical students from the other majors. The box part of the box plot for the business sample does not overlap with the boxes of the other box plots. This suggests that business majors as a population may have a lower mean frustration score overall. In the language of hypothesis test, we reject the null hypothesis and conclude that the population mean frustration levels differ. By contrast, in scenario 1, the typical scores in each sample are similar despite the same differences in the sample means. Even though the business sample has a lower sample mean than the other groups, there is overlap in the boxes of the box plots for all 4 groups. This suggests that the differences in the sample means are not indicative of differences in the population means. In other words, the 4 samples look like they could come from populations with the same mean, perhaps a mean of around 12. The differences we see in the sample means could be due to chance. In the language of a hypothesis test, we fail to reject the null hypothesis, H sub 0. The sample evidence is not strong enough to conclude that this population mean frustration levels differ. Okay, so now let's look at a summary here. Okay, the ANOVA hypothesis test answers this question. Are the differences among the sample means due to true differences among the population means, the alternative hypothesis, or merely due to sampling variability, the null hypothesis, which is basically the same question we've asked before, but of only 2 population means. Now we're looking at more than 2. It makes the formulas more complicated, the F statistic more complicated, but we're not going to worry about that in this class. In order to answer this question using our data, we obviously need to look at the variation among the sample means, but this alone is not enough. We need to also consider the variation of the data within the samples. The F statistic does this because it is a ratio of these variations, like we kind of talked about. We didn't give the specific formula, but we gave the idea that F is a fraction where the numerator is the variation in the sample means and the denominator is the variation in each sample. This ratio of variations is the idea behind comparing more than 2 means, hence the name analysis of variance, or ANOVA. When the variation within the sample data is large relative to the difference in sample means, like in scenario 1, the data provide very little evidence against. In this case, the F statistic is small, and as we have seen before, a small test statistic has a large p-value. When the variation within the sample data is small relative to the difference in the sample means, like in scenario 2, the data have stronger evidence against. In this case, the F statistic is large, and as we have seen before, a large test statistic has a small p-value. Now I'll make one final comment about comparing the F statistic to other test statistics like z-scores and t-scores. The F statistic has a different structure from the z-scores and the t-scores, but it is similar in that it's still a measure of the evidence against the null hypothesis. As with other test statistics, larger values of F give smaller p-values. The larger your F, the more evidence we have against H sub 0 or the null hypothesis. Lastly, if F is large when the denominator, the variation of the data within each sample, is small relative to the numerator. So when the variation of the data within each sample is small, but the variation among the sample means is large, that's when you'll get large F statistics.